Okay, so outside a finite set of points, what's going on is the map moves points around, but it also takes this grid pattern and it shrinks in one direction and it contracts in the other direction. So this expansion factor, it's also called maybe expansion factor, is kind of a measure of the complexity of the mapping class. It's sort of like, imagine you're on this, you take the surface, you want to know how much are things getting stretched around and moved around. And also log of this is the minimal entropy amongst all the members of the mapping, minimal topological entropy amongst all the elements of the isotopy class, for those of you who like entropy. So it's a topic of interest. So some questions: which lambda can occur? What are its properties? And how small can lambda be for a fixed surface? And what do small, so these are actually 3 questions, I guess. What do small dilatation maps look like? Okay, so those are some motivating questions. Okay, so now let's consider, so you have pseudo-Nosov maps. They're subsets of the mapping class group. The mapping class group is defined for a fixed surface, but we're talking about some kind of dynamical thing, and there's a lot of theory that makes so that you can encapsulate the dynamical situation in terms of something combinatoric. So let's consider, given these questions, let's consider the set of all pseudo-Nosov mapping classes. So this is, just let S vary and look at just all pseudo-Nosov mapping classes altogether. So this is just some messy set. It has no topology on it. Mod S has nice structure, which a lot of people study, but we're just going to take the whole mess of it together and make us take the union of this thing. So then this is in order to study dilatation. Okay, so then the goal is, it will be useful to put a metric topology on P. So you have a notion of when are two things close somehow in terms of their dynamics without fixing S. So it's a strange idea, if you sort of want to work on one surface, you have to go to another surface to find something that has similar dynamics. But what I'm going to talk about is something that allows you to do that. So we want the metric to have the property that nearby points have similar dynamics, whatever that means. And so in particular, lambda or log lambda behaves nicely. And lambda is computable, is always nice. And with these kinds of tools, maybe we can attack these problems. Okay, so we can do this by using fibered phase theory. That's what fibered phase theory helps you to do. Okay, so fibered face theory, or cone theory. Okay, so let M be a hyperbolic three-manifold. So we go up one dimension. Then Thurston defined a norm on the first cohomology of M with coefficients in R. So that's R to the first Betti number. And this has the property we call the Thurston norm. And I'm just going to say what the properties are instead of saying how to define it. The unit norm ball is a convex polyhedron. For each top dimensional face, F, let's call this B, of B, either all the primitive integral points in the cone over the face, which I'll call V, is induced by a fibration M to S1. Okay, so remember, if you have a fiber bundle of M to S1, then you have a map on fundamental groups, surjective map on fundamental groups. So you have a map from pi 1 of M to Z. That defines a cohomology class. And so we say a cohomology class is fibered if it was induced by a fibration. Okay, so either all of the primitive integral points, primitive just means that it's so you have a rational ray through the fibered face, and it's the smallest integer point on that ray. So either all of these are fibered or none of them are. None of the points are fibered. Okay, and we say that in case 1, we say F is a fibered face and V is a fibered cone. Okay. Okay, so now we're talking about different fibrations of a three-manifold. And say the first Betti number is bigger than or equal to 2, then the faces of the polyhedron have to be dimension at least 1. And each rational point on a fibered face has at least one, it has a primitive integral point associated to it. So I'm going to show you an example when I flip this board, but maybe I should just sketch for you. So what you should picture is if M has a fibration to a circle, then there is at least one fibered face. This fibered face has dimension, the first Betti number of the three-manifold minus 1, and for every rational point on here, there is a primitive integral point, and that also corresponds to a fibration. Now, I should say another property of this norm is that if alpha is fibered, the norm of alpha is just the absolute value of the fiber of the fibration. So there's an associated psi alpha from M to S1, and the monodromy is some mapping class, and the norm is just, which is how far it is out. So this length here, if this is alpha, is equal to the Euler characteristic of the surface. And that is in turn, if you look at the fibered face, it's the denominator of the point. It's a rational point on the fibered face. It's the denominator of that point. So you can see that not only do you have, so if M is fibered at all, and first Betti number is bigger than or equal to 2, that means that M is fibered in infinitely many ways, and the fibers have unbounded Euler characteristic, topological Euler characteristic. Okay, so this gives you a natural family of mapping classes where you're not fixing the surface at all. Now there's a result of Thurston that says SV is pseudo-Nosov if and only if it's mapping torus, which is the thing that fibers to give you that monodromy, if and only if this is hyperbolic, if that 3-manifold is hyperbolic. So, so this fibered face theory gives a partition defines a partition of the set of all pseudo-Nosov mapping classes and a metric topology and a metric, well, I'll just say metric topology. So just by sort of the basic, this is in Euclidean space, and you have this Euclidean topology induced on the fibered face, and then each of these rational points are the corresponding to different mapping classes. Okay, so you have F. The rational points on F are in one-to-one correspondence with elements, some subset of P. And so the topology on this gives you a topology on that. And then P is a union of all those B's. Okay, so that gives you the metric. Okay, so that's nice. We just have a way of partitioning, so we have a little bit of structure. But we want to know, I mean, so how useful is this? So Fried showed that so given a fibered face, a fibered cone, the function dilatation of the corresponding, so for alpha, so this is V, for a primitive integral element of the fibered cone, lambda phi to log of lambda phi extends to a convex continuous function on all of V, homogeneous of degree -1 and going to infinity toward the boundary of V. Okay, so now these primitive integral points are kind of scattered around like this, but we can extend by using, first of all, once we decided that it ought to be homogeneous of degree -1, we can extend to all the rays, and then we can, that means it's defined on all the rational points, all the rational rays, and then we can try to extend it. But it turns out that the function is actually extends to a continuous function, a nice convex continuous function, and it goes to infinity toward the boundary. So it defines on F, if you just restrict it to F, it gives you a map that looks like that. It has a unique minimum. So this defines taking the exponent, a continuous convex function on the fibered face. Let's call this L, and maybe I'm probably going to, let's just call it L for now. A function which is like this, which we can think of as the normalized dilatation. So take the dilatation raised to the Euler characteristic power. It defines a continuous convex function that extends this function for alpha. I'm kind of mixing up notation a little bit for alpha rational on F. Or maybe I should write, this is alpha bar, like that. Okay. What did I do with the eraser? Here. Okay, so this is doing those goals that I said before. Dilatation behaves nicely. Log dilatation behaves nicely. There's more to it, which I'm not saying. There's been a lot of study about how exactly the dynamics are related. But one of the outcomes is that the dilatation behaves nicely. Now, for computability of the dilatation, McMullen showed that if V is a fibered cone, there exists a sort of polynomial where H is the first homology of the manifold modulo torsion, such that for alpha primitive integral we have lambda of phi alpha is equal to, so I'm going to write it down and then I'll tell you what I mean, but you can just get it from that polynomial. Okay, so what I mean is alpha is an element of cohomology. So alpha defines a map from H to Z, because it's a primitive one. And theta is an element of ZH, so you can write that as the sum of A sub G, where G is in some support, is some finite set, subset of H, and A sub G are integers. Okay, so theta is some element in the group ring. You can write it like that. Specializing at alpha just means you take this and you make it into a polynomial in one variable. You just take the same coefficients and you raise it to alpha of g. Alpha of g is now an element of z. So this actually, it could be a Laurent polynomial. It could have negative powers. But let's not worry too much about that because we're interested in the roots. So what I mean by if p of x is a polynomial, then by this I just mean the maximum amongst the norms of the roots of p. So even if they're negative powers, we're just interested in the numerator part, and so if you multiply by x, we're going to get something that's a polynomial, and then we can ask what's the largest root of that. So lambda can be written in this way from one polynomial that just depends on v. Now it's a little bit similar to homological, the properties of Alexander polynomials. So we can compare given m, you have an Alexander polynomial, a multivariable Alexander polynomial. This is also an element of ZH. And if we take alpha in a fibered face, primitive integral, then the homological dilatation, so lambda hom of phi alpha, is just the specialization of the Alexander polynomial and the largest root of that. Okay, so it kind of, this is called the Teichmuller polynomial. The Teichmuller polynomial, although it was defined by McMullen, and a lot of people think maybe it should be called the McMullen polynomial. But this Teichmuller polynomial kind of is like playing the role of the Alexander polynomial, just measuring the geometric dilatation rather than the homological dilatation. The interesting thing is, though, that the Teichmuller polynomial is defined for a fibered cone, and a single three-manifold could have different Teichmuller polynomials for different fibered cones. Okay, so it's not just the one, whereas that three-manifold has only one Alexander polynomial. Okay. So are there any questions about this so far? It's a sort of quick run through of what we'd like to emulate. And let me just kind of summarize. If you started with a pseudo-Nassau map, for example, that you're interested in, and you want to know, okay, are there any similar ones? I want to study the ones that are similar. From that, just from the one, there is a unique three-manifold and a unique fibered face that it sits on. You can compute a polynomial. So there's a way. This is very computable once you know the train track. So there's a little, but you can compute this thing. It's an actual polynomial in several variables. And what's interesting is when McMullen defined theta, he also showed how to compute it. And if you go, look at how it's done, this thing actually defines a cone, because theta defines its own norm that which goes as follows, actually. So whereas before it had to do with the Euler characteristic of surfaces dual to the cohomology element, here we just say, okay, this is for alpha. Just think of alpha as always giving you an element of a map from H to Z, or even from H to R. H is the first homology. It's just saying, we can define a norm by saying, taking the maximum of the values of alpha at elements of the support of theta. So GH are in the support of theta. This gives you a convex, the unit ball is a convex polyhedron. You can look at, there's one face that corresponds to this SV, and so you get a cone this way, the cone over that face of the unit ball defined by this norm. Now this norm is not the same as the Thurston norm, but it gives you the same cone. So we get a cone, and this cone, remember on this cone the, so you get some kind of cone. We know that the dilatation function looks like this. It goes to infinity toward the boundary. If we just look at this, I mean, after all, because this is computing the dilatation, log of, we can just think of it as this function. We don't even need to know about what the other things look like. It's just a combinatorial thing coming from the polynomial. This function goes to infinity toward the boundary. That's how this defines the cone, actually. And so, let's see, what's my point here? Yeah, so somehow it says that you couldn't possibly, if dilatations are to make sense, if you take an alpha on this cone defined by theta, it couldn't possibly be fibered, because it wouldn't make sense. It would have to have a dilatation, and what could it possibly be that's blowing up there? So somehow it's just this polynomial is encoding a lot of the geometry that's going on in the three manifold. And that's kind of the principle that we're going to employ. Now I want to give an example really quickly just to show you how nice fibered face theory can be. So let's see if I can. So, let's take the mapping class, take S to be a disk minus 3 points, or a disk with 3 disks taken out. And so let's rotate these two around like this. Actually, we usually go the other way, I guess. So just kind of rotate and pull things around with it. And then, so you rotate like this, and then you rotate the other one. So you do this first, and then you do this second. And that gives you a mapping class on the sphere minus 4 with 4 boundary components. Okay, so you start with one mapping class. And then, so I'm not going to show you the work that's involved, but it's kind of a fun thing to try to do. You can, from that, well, you know that if you draw what's going on, the mapping torus is just S3 minus this link. It's got to be S3 minus this link, but that's the same as S3 minus this. You could redraw this so it looks like this, and it's completely symmetric on both sides. That means that your fibered face is going to be very symmetric. You can also look at, you can figure out what the Thurston norm is. Okay, so there's some work here, but it's fun to work through it. It's not hard to do. And you find that the norm is given by this. So here's a unit norm ball. It's going through 0, 1/2, for example. And so here are a bunch of primitive integral points on the fibered cone, on a cone. And 0, 1 corresponds to this mapping class, and you have others. Okay, and here's the Alexander polynomial, and here's the Teichmüller polynomial. Okay, and I can say a few things really quickly. I mean, this is the fun part, but I know I'm also running out of time. How much time do I have again? 8 more minutes. Yeah, okay, I'm not going to get anywhere. But let me just finish this. And but I think this is just such a nice story. And it's probably more to people's benefit to know this story in a way than to... Okay, so, but I'll maybe state real quickly how you can generalize this. But so this plays into the other question was how small can lambda be, and what do mapping classes look like? Well, so here, if the dilatation is 3 plus square root of 5 over 2, it's the golden mean squared. And actually, I was wondering why is there the title golden braid? But I mean, I don't know what it is, but it probably has nothing to do with this. But this could be thought of as the golden braid because but anyway, so its dilatation is the golden mean squared. And this one is the smallest known genus 2 dilatation. This realizes the smallest genus 2 dilatation. It's been confirmed that that's the smallest. Very little is known about what is the smallest dilatation for any particular surface. In fact, it's only for closed surfaces, it's only known for genus 2. But for orientable, there's more known due to work of Leno and Tifo. And so these give you the minimum for genus 2, 3, 4, 5, and 8. Okay, so let me stop here. I mean, it could go on and on. But let me just try to... So I've been hinting that a lot of stuff comes out of combinatorics. And, oh, and by the way, why do so many small dilatation things happen for the 1-3 manifold? There's a result of Farb, Margalit, and so two of them are here, and Leininger, that says that if you bound the normalized dilatation, then you only need to look at a finite number of 3 manifolds. That implies, for example, that there is a minimum normalized dilatation, which I think is really interesting. So there's a conjecture that the minimum accumulation point for lambda phi to the s, if you know as phi and s ranging in p, is 3 plus square root of 5 over 2 squared, and it's attained at this point exactly, and but Farb, Margalit, and Leininger theorem says that the minimum is attained because you only need to look at some finite set of 3 manifolds. Nobody knows how big that set is, but it is attained, and so here's a conjecture. Okay, so let's see. What I want to write a formula. How about if I just try to finish with a formula? Okay, so let's just talk about a directed graph, D. So I'm going to get into the combinatorics. So a directed graph, you have some vertices, you have some edges with some arrows on them. So let's do something like this. This is very silly. This has a directed adjacency matrix, which has entries for directed pairs. So, for example, if this is the first vector and this is the second vector, the first vector is 2, 2, and the second one is 1, 1. Okay, so there's a digraph, there's an associated adjacency matrix, and for simplicity, we can just say, okay, lambda of D is just the largest eigenvalue, the spectral radius of A. Now D is called expanding. It's sort of the thing that's associated with, it tends to be associated with things that are pseudo-Nosov or other kinds of nice expanding dynamics. D is expanding if it is strongly connected. So it's a very simple thing to check. It's just if you can get from any vertex to any other vertex by a directed edge. Maybe by more than one, sorry, directed path. Okay? And then, so the characteristic polynomial of this thing, if somehow this came from a pseudo-Anosov map, the characteristic polynomial, the largest root of the characteristic polynomial would give you the dilatation. Okay, so the characteristic polynomial, so classical fact is that the characteristic polynomial is given by some kind of interesting function. It's, let me just write it down. So there's this, so given a directed graph, there's an associated curve complex or cycle complex. A cycle is something which is is a loop on the graph that doesn't pass over any vertex more than once. Let's see, I guess sometimes we call it, so a cycle, that's a connected cycle, but also you could have loops like this which don't intersect. So you could have more than one component. Okay, so this is a set of cycles, and it could be a union. It could have different components, so the number of sigma is the number of components, and L of sigma is the number of vertices it passes through. And here we have n is equal to the total number of vertices. Okay, so this has a nice formula. And exploring this, McMullen showed that for D with certain properties, just that this polynomial is reciprocal, which always occurs in the pseudo-Anosov case, he showed that 3 plus square root of 5 over 2 squared is the smallest dilatation you can have, normalized dilatation. So this is less than or equal to the dilatation to the number of vertices. Okay, so you can kind of do this for free bicyclic groups. And so it just means now now replace S by Fn, or think of you're acting on the fundamental group. Basically, so in joint work we showed that there is a Teichmüller polynomial for the free bicyclic group case, and it's not just, our method doesn't just mimic the methods for in the mapping class situation. We exploit the combinatorics, and we make sort of a digraph, a directed graph, which is like a train track for the sort of semi-flow defined by a free group automorphism, and we show that if you take the dual digraph of that, you get a similar formula. So for every cycle on the directed graph, since this directed graph is living on a 2 complex associated to the group, so this group you should think of as like the fundamental group of the 3 manifold. Using this has the property that when you specialize, you get the right dilatations. Okay, and so it's kind of evocative because again it's this alternating kind of sum, and also what's interesting about this is that this is a finite complex. So it sort of shows that there are these special transverse, there's sort of special orbits in the flow, only a finite number of them, which is telling you exactly what the dynamics is, whereas most studies think of it as this much more complicated thing. You can even describe it as some sort of train tracky directed graph, and so that's an area that's to be explored more. So I'm very sorry about going over. I'm not sure what the topology, what is the topology? I mean, oh, you see, okay. You mean on the three manifold itself?
Yeah, the set of three manifolds and the topology.
Oh, the set of three manifolds, yeah, okay. Yeah, I'm not, I don't know. That's a good question. But yeah.